Ever wondered how scientists make sense of data that's way more complicated than a simple yes or no? Imagine trying to predict something deeply personal, like your risk of a disease, using both your unique genetic code and basic medical info. But here's the catch. Your DNA has millions of data points, while your doctor's notes might just have a few numbers. How do you even begin to compare them? That's where pre-validation comes in, a clever technique to balance the chaos of complex data with the simplicity of traditional tests. Let's break it down. Pre-validation is like a two-step dance. First, you take that massive, messy genetic data and use it to make predictions about outcomes, like whether someone might get sick. But here's the catch. You don't throw all the data at a model at once. Instead, you leave one person's data out at a time, train the model on the rest, and use it to guess what the missing piece might be. It's like testing a recipe, by tweaking ingredients one at a time to see what works best. Then in the second step, you mix those predictions with simpler stuff, like age, blood pressure, or family history, to build a final model. This keeps the complex data from drowning out the simpler, more straightforward info. But here's the problem. When you check if the genetic data actually adds value, the usual math doesn't play nice. The results don't fit the standard bell curve we're used to. Why? Because genetic data and clinical data are tangled together in ways we don't fully understand. Earlier studies showed this messes up the math behind hypothesis testing, like thinking a result is meaningful when it's not. This paper fixes that. They relaxed the old rule that data sets are independent and came up with new math to handle the real-world messiness. They also introduced a bootstrap method, a fancy term for repeating the analysis many times with slight changes to get more reliable results. And the proof? They tested it on real data, like a breast cancer study, and even made up some fake genetic data to see how it holds up. The results? Pre-validation isn't just fairer, it gives better predictions and more accurate error estimates. So next time you hear about breakthroughs in personalized medicine or genetic research, remember, behind the scenes, scientists are wrestling with these data balance problems. And tools like pre-validation are the unsung heroes making it all work. Want to see how this plays out in a real experiment? Stick around, we'll dive into the numbers next. Hey there! Ever wonder how machines learn from data without going off the rails? Today, we're unpacking some mind-blowing math that keeps complex models from crashing and burning, no matter how much data they're fed. Let's dive in. Imagine you're building a model to predict something wild, like stock prices or weather patterns. But here's the catch. As you add more data, things can get weird. Numbers might explode, predictions could go haywire, and suddenly your model is as reliable as a toaster in a hurricane. How do we stop that from happening? Enter the determinant, a special number linked to matrices, which are just grids of numbers. A positive determinant. That's a good sign. It means the matrix is invertible, like a puzzle piece that fits perfectly. Without this, your model could collapse, like a house of cards in a storm. But here's the magic. This research shows certain matrices stay stable, keeping predictions from going off the rails. Now let's talk about spectral decomposition, a fancy way of breaking down matrices into their core parts. Think of it like disassembling a robot to see what makes it tick. The researchers found that the strength of these matrices, called singular values, stays below 1, like a governor on an engine. This keeps everything from blowing up, even as datasets grow huge. But here's where it gets really clever. They tested what happens if you tweak the data, like removing one data point. Using tools called operator norms, they proved these tiny changes become negligible as the dataset grows. It's like adjusting one brick in a skyscraper, the whole building stays standing. And then there's the real kicker, approximations. They define terms like high and newy as building blocks for predictions. As the model scales, these approximations get closer to the truth, like a GPS that updates itself in real time. No more guesswork, just steady, reliable results. So what's the big deal? This isn't just math for math's sake. It's the backbone of models we trust every day, whether it's recommending movies, diagnosing diseases, or forecasting the weather. By proving these properties, researchers are giving us tools to build smarter, safer systems. Next time you see a machine learning model in action, remember, behind the scenes, math is working overtime to keep things from falling apart. Thanks for watching. If you want to see how this applies to real-world tech, hit that subscribe button. Until next time, keep exploring and stay curious.